In the prior video, we found the equation of motion for a 1 degree of freedom system, and here in this video, we're going to find the equations of motion for a 2 degree of freedom system. So let's just outline what the problem is. So we have a cart that can move along on the horizontal ground. It has a mass, but we're going to assume that all of that mass of the cart is concentrated at a single point C, and that it has a mass of mc. And this will allow us to treat the cart as though it is a particle. In addition, so at point C, we also have an attachment of here we have a massless rigid rod, and then here we have our a particle P, and that has a mass of mp. And this rod and particle can rotate or pivot about point C. In addition, we have a force, F, that's being applied to the cart, as drawn here. So let us draw our reference frames to start out. So we have, I'm going to put my fixed frame A here. So this way I can describe, say, the motion of C in using one unit vector. And because this rigid rod attached to particle P can rotate, again, we're going to define a second rotating reference frame, frame B. And now that we've outlined everything in our example, our goal is to find the equations of motion for the system. And so we use the following steps to do that. So first, we write down the degrees of freedom of this system, which I kind of spoiled in the very beginning of this video as 2 degrees of freedom. And that's because the cart can move in the horizontal direction, so that's 1 degree of freedom, and then the pendulum, so that rod and particle, right, that can rotate. So that's our 2 degrees of freedom. And for our coordinates, we have, so we can describe the translation of the cart in the horizontal direction using the variable x. So I'll put x here. And then if we can define the orientation or rotation of this rigid rod with the particle attached, that's going to be theta. So our second coordinate is theta. The next step is to draw our free body diagrams. And I say diagrams because we have two masses, right? So we have C and we have P. So we have to draw two free body diagrams. So if we start with point C, so our mass C, we have a gravitational force being applied. So that's mcg. Then as drawn here, we have a force that's directly being applied to the cart, F. We have our normal force from being in contact with the ground, and then we have a force from the particle, from the mass of the particle through this rigid rod. So you can think of that as tension, so we'll call that T. In addition, we have the, to draw a free body diagram for particle P. So here we have P, and then of course we have our gravitational force, so that's going to be mpg. And then we have, again, our tension, right? So now it's just operating in the opposite direction, T. Again, that's acting along the rigid rod. So now that we've drawn our two free body diagrams here, we can actually write these force vectors out. So up here, I'm going to put a third step, which is write FP and FC. So we'll start with the longer one. So we have Fc is equal to, and so we'll start with our tension T. So that is operating in the B1 direction, so we can write TB1. And then we have N in the vertical direction, so we can write that as NA2. And then we have a force, our force F, being applied in the A1 direction. And then we have our gravitational force mcg operating in the negative A2 direction. And then for the forces on particle P, we have two. So we have, again, this tension, but now it's in the negative B1 direction. And then we have the gravitational force in the A2 direction. So now that we've written out our forces, we have to now write out our accelerations. So we need to write the acceleration of point C in frame A and point P in frame A. So we'll start with, again, the easier one, which is the acceleration of C in A. So we'll start out by just writing our position vector ROP is equal to XA1, so that means our velocity, C. Sorry, these are both C. Our velocity of point C in frame A is equal to X dot A1, and then our acceleration of point C in frame A is now X double dot A1. So now we can write the position vector for ROP, and that's going to equal X of A1 plus LB1. And we can, I'm going to use the magic formula here. So I'm going to write the velocity of point P in frame A. So this is actually going to be X dot A1. And plus, I'm going to skip a few steps here. All right, so the time derivative of this is 0, right? L doesn't change. Oh, I should say I wrote L. L is the length of this rod here. L doesn't change, so that's 0. And what we're left with is the cross product between theta dot B3 and LB1 here, this position vector, which is going to equal L theta dot B2. And then we can use the magic formula again, and we can get the acceleration. I'm just going to skip right to the answer here. This is L theta dot double dot B2 minus L theta dot squared B1. Okay, so now we have our two acceleration terms. And so with that, we are now going to use Newton's second law in order to relate the accelerations and the forces. So second law, and so again that is, I'm just going to write the generic form up here, so that's Fp is equal to m, the acceleration of point, acceleration of point P in frame A. Okay, so for particle C, or for the cart, we have we've got TB1 plus Na2 plus Fa1 minus mcg A2, and that is equal to mc times x double dot A1. And now if we write down the forces on particle P, we have negative TB1 minus mpg A1, and that is equal to MP x double dot A1. And so I'm just writing out the, distributing the MP terms. So MP L theta double dot B2 minus MP L theta dot squared B1. Okay, so we had 2 degrees of freedom, so ultimately we're going to get 2 equations, one for particle C and then one for particle P. Okay, so just like last time, I'm going to clear the board here, and then I'm just going to rewrite what those 2 equations are. All right, and they magically appeared quickly. Okay, so now we can move on to step 6, which again was to rewrite all the terms in the same frame, so in terms of the same unit vectors. So all terms, same frame. And so here looks like we have a lot more A1 and A2 terms than B1 and B2 terms. So we're going to switch everything into terms of A1 and A2. So to do that, we use the following relations. So we have B1 and B2 are equal to cosine theta sine theta minus sine theta cosine theta. And so this is A1 and A2. So again, we can write this out as B1 is equal to cosine theta A1 plus sine theta A2, and B2 is equal to negative sine theta A1 plus cosine theta A2. And so now we just plug those in where necessary, right? So here, 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 and here. So we rewrite this first equation as T cosine theta A1 plus T sine theta A2, and then everything else is in terms of A1 and A2 already, so that one's quite easy. NA2 is FA1 plus MC x double dot A1. So now we have the second equation. So we have negative T cosine theta A1 minus T sine theta A2 minus MP G A2 is equal to MP x double dot A1, and then we have plus MP L theta double dot. So this is actually going to be a, this will be minus sine theta A1, and then we have plus MP L theta double dot cosine theta A2, and minus MP L theta dot squared cosine theta minus MPL theta dot squared sine theta. Oops, and then this is, sorry, this is A1 and this is A2. All right, so we got 2 pretty long equations here. So now we're going to take each of those equations and then we're going to separate them into their A1 and A2 terms. So I'm going to put separate A1 and A2 terms. Okay, so we'll start with the first equation. So we'll call this one, this is just equation 1, this is equation 2. I wanted to use different colors. 2. Okay, so for equation 1, we have our A1 terms. So we have T cosine theta plus F, and that is equal to MC X double dot. In terms of A2 terms, we have T sine theta minus mcg plus n. And there's no A2 term on the right-hand side, so we set that equal to 0. So that's for that first equation. Now we have our second equation. So we have A1, in terms of A1, we have negative T cosine of theta. And then we have everything on the other side. So we have so we have MP X double dot minus MPL theta double dot sine theta. And then we have, whoops, that's right, sorry. And then we have minus an MPL theta dot squared cosine theta. All right, so again, that's 1, 2, 3. Okay, and so now we have the A2 terms here. So now we have negative T sine of theta minus MPG, and that is equal to, we have here MPL theta double dot cosine of theta minus MPL theta dot squared sine of theta. So what we've done here in step 7 is now we have 4 equations. And it turns out that we have 4 equations, but we also have, 4 equations. We also have 4 unknowns in these equations. So unknowns are, we have X, right? And we also have theta. We also have T, right? We don't know what T is. And we also have an N in there. So if there's T, there's an N, N. And what we ultimately want is we need to get 2 equations where the only unknowns are the coordinates X and theta and their derivatives. And so we're going to now, out of these 4 equations, essentially get to that. So again, a quick clearing of the board, and I kept our 4 equations here. Again, we have our 4 unknowns. And like I said, ultimately what we want are 2 equations. So I should just write that out here. So what we want are 2 equations with only X and theta and their derivatives. Those are the only unknowns that should be in those equations. So now we just kind of mess around and see if we can get there. It's actually not as hard as it might seem at first. What you might notice here is if we look at this first equation, we can write an expression for t. So we can just simply rearrange this. And so now we can write that t is equal to mc x double dot minus f divided by cosine of theta. And you may also notice that in these last two equations, we only have unknowns of t, x double dot, or sorry, t, x, theta, and the derivatives of theta and x, right? And so now that we have an expression for t, we can plug this in to here and to here, and we can get rid of the t's, and so now we are left with, would be left with two equations that will only have x and theta terms and their derivatives. So let's actually go through and plug that in. So we have this first equation, so I'll put 1 here. So 1, we have negative, and then t is mc x double dot minus f over cosine theta times cosine theta is equal to, we have mpx double dot minus, just move that minus sign down here, so minus L theta double dot sine theta minus MPL theta dot squared cosine theta. And then our second equation is negative, and then again we substitute in for t, mc x double dot minus f over cosine theta, and this is sine theta minus mpg, and that is equal to mpl theta double dot cosine theta minus MPL theta dot squared sine theta. All right, so now we just have to simplify. So again, we'll start with equation 1 here. So we can cross this out and cross this out here. So we're left with negative MC x double dot plus f is equal to px double dot minus MPL theta double dot sine theta minus MP L theta dot squared cosine of theta. And then our second equation, so sine of theta over cosine of theta is actually equal to tan of theta, so we can write this as negative, we have negative MC x double dot plus f tan of theta minus our MPG is equal to MPL theta double dot cosine theta minus MPL theta dot squared sine theta, right? And so that's equation number 2. And we're going to do one more simplification, and that's, again, as I mentioned, by convention, we want to bring all of the coordinate terms, so our x, our theta, and all of its derivatives over to the right-hand side. And then what we're going to do is we're going to bring anything else, so any other force terms, we're going to bring that over to the right side. So for instance, I'll write this in neon yellow because this will be the final form. So we have negative, and I'm going to combine terms as I'm going along. You can follow how I did this in the worked sample problems. So we have here, oops, so we have MC x double, oops, sorry, the whole point was to simplify. So we have MC plus MP x double dot, and then we're going to have minus MPL, and then here we have theta double dot sine theta minus theta dot squared cosine theta, and that is going to equal F. This one takes a little bit more rearranging. We have to divide by tangent. But again, if you work it out, what you will ultimately get is the following. So we have mcx double dot plus mp, and that's times L theta double dot minus L theta dot squared plus G over sine theta all times cosine theta, and that is also equal to F. So again, now we have, these are our two equations of motion for our system. All right? And when we solve this, ultimately what we would want to find is a sequence or series of theta values and a series of x values that when you plug them in, plus you plug in their derivatives, so the first and second derivatives, all these equations are satisfied. And so that is it. Like I said, in the first video, you did your first equation of motion. Here's your second equation of motion. And so we're just going to keep practicing this throughout the homework problems, and then we'll start to see, hopefully you'll get into the habit where you don't need to actually write out like what the steps are, but continue to do so as much as that's useful for you. But these are the general, this is the general approach we're going to use for the next week or so for solving our equations of motion.